Welcome to all. So I am Nagarajan, Assistant Professor of Physics, Government First College, Kolar. This is about Bangalore North University third semester BSc Physics, paper Electricity and Magnetism. And the learning objective of this session is so your students can easily understand the magnetic field and forces. Expression for equation used to calculate a magnetic force for an electrical wire placed in a magnetic field and the definition of Lorentz force. So after the completion of this session, someone can easily recall or remember the concept of magnetic field and forces, the force in a moving charge, and here students can recognize the moving electrical charges generate a magnetic field and also the concept of Lorentz force. So before going to the actual topic, we need to understand some basic terminologies. So how the charged particles moves in a magnetic field. So this is a uniform magnetic field. This is a uniform magnetic field. A charged particles is placed in a uniform magnetic field. Now, here the charged particles moves with a velocity v perpendicular to the magnetic field, and here the force is always directed towards the center of the circular path. This is a circular path. Always the magnetic force is always directed towards the center of the circular path. The magnetic force causes a centrifugal acceleration, changing the direction of the velocity of the particle at every point. See here, that means when a charged particle is placed in a magnetic field, the particles follows a circular path. This is how the charged particles moves in a magnetic field. And the other basic information related to this topic is an electric field is a region in space where an electric charge at rest experiences. So that's a basic definition of electric field. When an electrical wire is exposed to a magnet or placed in a magnetic field, the current in that will experience a force that results in a magnetic field. That means when an electrical wire is exposed to a magnet, the current in that wire will experience that results of a magnetic field. When a positively charged particle moves in a uniform magnetic field, then the direction of the velocity of the particle is perpendicular to the field that already shown in the diagram. The magnetic field force always acts in a direction perpendicular to the motion of the charge, that also are shown in the diagram. The space or the region around a magnet within which the magnetic force is exerted on the other magnet is called magnetic field. This is a basic definition of magnetic field. So now we will move on to the actual topic: force on a moving charge in a uniform magnetic field. In a magnetic field. So consider a charge Q. Q is a charge. Whatever may be the charge is placed in an electric field of intensity E. Then the force experienced by the charged particle F is equal to Q into E. So the force experienced by the charged particle is F is equal to Q into E, where Q is the charge, E is electric intensity. But in space, where the magnetic field exists, the charge will experience its force only when the charge is in motion. Then the magnitude of force depends upon the speed of the motion of the charge. The magnitude of the force depends upon the speed of the motion of the charge also. It is considered a magnetic field V. Magnetic field V, in which charge moves with a uniform velocity V. This is a uniform velocity in a magnetic field V. Then the magnetic field experienced by the charge V, F is the magnetic field experienced by a charge. Then the magnitude of the force experienced by the charge particle is directly proportional to the charge, and the magnitude of force is also directly proportional to the velocity component, which is perpendicular to the magnetic field, and also the magnitude of force is also directly proportional to the magnitude of the magnetic field. So if you combine these three factors, then Fb is equal to Q into V cross V, or F is equal to Q B sin theta. So these equations indicate that force experienced by the charge under the influence of magnetic field, and theta is the angle between the velocity and the magnetic field. So we got this equation, f of b is equal to q b sine theta. If theta is equal to 0 degree or theta is equal to 180 degree, then sine theta is equal to 0. So in this equation, either theta is equal to 0 degree or theta is equal to 180 degree, then sine theta is equal to 0. Therefore, Fp is equal to force experienced by charged particles in a magnetic field is 0 or minimum. That means a charged particles moving parallel to the direction of the magnetic field does not experience any force. The charged particle will continue to move along the line of the force. That's the meaning of this condition. Next, we will move on to another condition. If theta is equal to 90 degree, then sine theta is 1, Fb is equal to QB, or the charged particle experiences maximum force when it moves along the perpendicular direction of the magnetic field. When it moves along the direction of the perpendicular direction of the magnetic field. The next condition, if V is equal to 0, then Fb is equal to 0. There is no force acting on a charged particle when it is at rest in a magnetic field. That's the meaning of this condition. There is no force acting on a charged particle when it is at rest in a magnetic field. And if you come to the Lorentz force under definition of B, so Lorentz force is the combination of force experienced by charged particles moving both in the electric field as well as magnetic field. Let us consider a particle of charge Q moving with a velocity v in the electric field of intensity E and a magnetic field B. Then the net force acting on a charged particle is equal to Lorentz force is equal to electric force, sum of the electric force plus magnetic force. The Lorentz force is equal to the resultant of electric force and magnetic force, or sum of electric force and magnetic force. Therefore, this Lorentz force is equal to QE, this electrical force, plus Q into V cross B, this is the magnetic force. So if you come, therefore similarly F is equal to, if you take Q is common, you get this equation, where F is called Lorentz force. The component Q is called Lorentz electric force, and Q into V cross B is called Lorentz magnetic force. The magnetic field B is defined in terms of force on a moving charge in Lorentz force law. So that is F is equal to Q E plus QV cross B. So this electrical force, how electrical force experiences in this situation, and here the magnetic force of magnitude Q beside theta perpendicular both V and B away from the V1. So the conclusion here is you can understand the Lorentz force, magnetic field, and force in a moving charge, and the electric charge is generated magnetic field. And these are the references I have taken. Thank you.